Hey everybody, and thank you for joining us again for a live coding, hacking, whatever stream, our weekly Raspberry Pi Pico stream. First of all, as usual, just let me know in the chat if you can hear me and everything is fine. And meanwhile, I will go to share my screen. So, the horror. And by the way, hi Andreas, thank you for saying hi in the chat. Before we get into all of this stuff, which we left off last week, this is a good chance to say again thanks to Benny. I'm a bit confused. To Benny, who sent me a Raspberry Pi Pico, and thank you, Andreas, for the feedback. So now I know that my sound is working. So what I did during the week, I set up the Raspberry Pi Pico so we can use it if we want to debug anything. So let me share with you my setup. So this is the physical setup. So I have this Raspberry Pi Pico here, and it's connected with, so this is the debugging port of the Pico, and it's connected to another Raspberry Pi, which is taking care, it doesn't focus, but anyway, you can see there are like 3 wires that go from the Pico to the other Raspberry Pi, and that's how the physical connections are made. And if you want to follow this, there is like a great guide in the getting started document. So this is the the document we saw in the very first chapter episode of this live stream, where we I showed you how to set up, or I told you that you should do this if you want to compile the examples like I did. So apparently they also have a chapter about debugging, so how to install OpenOCD and how to make the connections to the Raspberry Pi. And I initially tried to use debug dongle, a ST-Link debug dongle that I had, but if you want to get it to work with the Pico, it doesn't, because it needs an patched version of OpenOCD, and they didn't do the patches for the ST-Link dongle. So basically, practically, the best ways to get a debugging setup is either to use a Raspberry Pi and follow this guide, or they have like a software where you can a firmware that you can flash that is called Pico Probe, and you can flash it into one Pico and use that Pico to debug the other one. So these are like 2 options that if you want to get your own setup. And after you follow the steps, you get OpenOCD running. So you can see I got it here in the terminal. Let's restart it. So you will see this is the OpenOCD running on the on this Raspberry Pi, not a Pico, the actual Raspberry Pi, and it's connected to this Pi Pico, and now it's listening on port 333 for connections, and then I can open a GDB connection. Let's do a new tab, and I can multi-arc or GDB multi-arc. Yep. GDB multi-arc, and then I can say target remote Raspberry Pi, and that was the port number 333. Let's make the font even larger. And yeah, you can see that now I'm connected to the Pi, and I can send commands like debug the code. Right now I didn't load the debugging symbols, but if I will load the debugging symbols, I will be able to see where it stopped. But you can also already recognize that this is like a flash address. And then if I type continue, it will keep running the code, and you will immediately notice that I flashed the blink code to the Raspberry Pi. And then if I Control C, then it will pause the execution in the same point. This is probably one of the sleep methods. And then I can like go instruction by instruction, which will probably get me into this loop. So you know what? Let's do something more interesting. Instead of just using GDB without the symbols, let's load the symbols. So the symbols, let's actually do it a bit differently. It's in the Pico directory, Pico examples. And then I rebuilt all the examples. So there is like, they have these instructions. You have to add this make cbuild type equals debug flag in order to get a flag build with debugging symbols. So I rebuilt all the examples, including the blink. And then if I go into blink, I can do gdb blink. Oh, that was gdb multi-arc. gdb multi-arc blink.elf target remote Raspberry Pi 333, and then you can see now it tells me where I am. I'm in the middle of alarm pool alarm clock, and then you know, I can set a breakpoint. Like first of all, if I write next, it will take me to the next line. Now oh, there is an issue with the debug connection. So those probes aren't the best. And sometimes connecting and disconnecting GDB causes problems. So let's try that again. Yeah, now let's see where we are. We are here in this same function, and actually we can set a breakpoint. I think that would be the easiest way to get to somewhere that we can recognize. So let's see, blink.c. We can break in like main on line 17. So that's blink.c line 17 before it, actually on line 19, before it switches this LED off. So we will be able to see that in the camera. So we can break on, that was blink.c line 19, and then continue. And yeah, you can see it actually set a breakpoint right after. So it stopped in the sleep right after it turned the LED off. And I can do layout src to see the source code, so to see where I am. And let's place another breakpoint. Yeah, you can see that it placed the breakpoint on line 20. And let's place another one on line 21. Let's see if that works. Blink.c21. No, it didn't work. Blink.c. Let's try line 16. Yep. And now if I continue, it should stop right. Where did it stop? No, it didn't stop where I wanted it to. Yeah, anyway, so I can try to do next, and hopefully it will run to the next something, but there might be some issue with, like, I don't know why the debugger stops in all these places instead of like taking me to the next line of code. But yeah, you can see that like now the LED is on, and if I continue until the breakpoint, it's off. So it sort of breaks in the right location. But anyway, the idea here is less to be able to debug code that we deploy to the Pi 0, and more to eventually let us compare what we have on the emulator with what we have on the physical hardware. For example, we have seen like the bootloader. So the bootloader, I think, is at I think it starts at this address, right, at the beginning of the flash. So maybe we can set a breakpoint there. Let's also, no, we need let's hide the code view for now. So let's set a breakpoint. We need a star, and let's also delete breakpoint 1 and 2. We don't need them anymore. And now we can I think it's monitor reset halt to just restart the chip. So go to the beginning. You see PC is now 00E, which is the beginning of the boot ROM, and then halt means don't run the program, so we can like stop at the breakpoint. It might have worked without the halt. I don't know. I haven't tried this before, but let's see. Okay, so it doesn't stop at a breakpoint, and the reason for that, if you remember, the bootloader is, first of all, it's copied from the flash into the SRAM, and then it's executed from the SRAM. So this specific memory address is never hit, and I think that at this point it would be like, maybe we'll do one more experiment. Let's just restart the thing, and then we can print PC. We can like you know, run the CPU step by step, like just see how the boot ROM goes. So we can see that we are here nowhere, but we can ask GDB to show us the disassembly, and then we can actually see the instructions. Like this is the very beginning of the boot ROM, the very first few instructions. So yeah, it's probably, it can go up for some reason, strange. Anyway, and then I can like step through the boot ROM and see which branches it takes, and you know, so this is basically, I'm seeing how the chip does the boot, and you know, I can keep running all the day. It will probably take a lot of time to go instruction by instruction. But this is just to show that this actually allows us to tap into the code and to see what it does on the real chip, and maybe it will be useful in the future, or hopefully in the not so far future. So I think that's about GDB for now. We have this setup working, and you have seen how we can use it. And let's do a big shift and go back to where we were last time. So let me see. We had this Visual Studio, and we had a few missing instructions. I think we had like we left a message in the to-do breakpoint. Do we need to implement that? Probably to reduce the noise. So yeah, so there is like this add instruction. Let's just copy them aside. Let's do them real quick, and then try to figure out what's still going on. All right, so let's start with this one, add R1 SP, and let's start with writing the test case. So all right, so let's start with the test case. All right, and that would be add, it should correctly code and whatever that was, add register SP plus immediate, I guess, instruction, expect whatever, let's call it opcode, add whatever, we'll see in a moment, R1, probably add SP. We already have as add SP2, so maybe that's add SP, but we'll see in a moment when we check out the datasheet. For to equal this number. Okay, cool. And now we can check the datasheet and see what it says about yep, about this add instruction. How is the encoding going? That was before, forgot. No, A67, yes. And that's add SP plus immediate, I guess, because we already did add SP plus register, right? That's the add SP2, I guess. Or maybe, oh, there is add SP with immediate and add SP with register. So that's one of them. So add, that's called add RDM, but 4 doesn't look like a register. It looks like SP plus immediate. So that would be add RD SP IMM7. I think that's the case. RD SP IMM. Yep. So let's call it add SP IMM. Right. Okay, and then or maybe this one should be, no, this is just add SP plus register. So this is like, yeah, let's make it add SP plus IMM, probably better. This is unreadable. Yeah, let's just call it add IMM and or add SP IMM. Yeah, or maybe, yeah, SP plus IMM. I think that's fine. All right, so let's implement it now that we finally agreed how, or I agreed with myself how I would call it. So export function add SP, and it gets RD number, IMM8 number, and then it does basically this, turn the thing shifted by 11, and then we can just copy from here because it's probably the same, like 3 bits of RD and then 8 bits of IMM. So RD, cool, and we have the function. Let's import it. Let's see that we indeed encoded the right opcode, and no, we haven't. Are we doing anything? Yeah, the usual trick, we need to 0 extend the IMM, or in this case, this means that we need to shift it to do the reverse when we encoding, shift it by 2, and now it passes perfectly. So yeah, so we have the encoding for this, and now let's do the test case for this. So rp spec ds, and yeah, let's just do a lot of copy paste. So in this case, add r1 spr4 will do let's say that in this case registers 1, let's say it equals 10, and sp 55. So after, actually no, it doesn't matter what value there is in r1 at the beginning, so we don't need that. We can just set it to 0, and this is like sp plus IMM, and we are at it into r1. So r1 gets let's say sp plus, yeah, let's keep it hexa. So if sp is 55, then after that we expect sp shouldn't change. We expect r1. Let's actually assert that it didn't change, and then this one should be 65, just the result. And interestingly, The test passes. Huh? How comes? Let's just focus on this one and see which code path it takes. I mean, the reason we added this instruction is because we concluded last time that it wasn't. Oh, of course, my bad. I should have asserted that it equals, not assigned a value to equal this. Yep. Now it doesn't pass, which makes me happy because it means that yeah, that's what we expected. And then add SP register, or how did they call it? Yeah, that's SP plus immediate. So let's call it add register SP plus equals SP plus immediate. And then if the opcode is this and shifted by 11, then we had somewhere we could copy this. Never mind, it will take a moment to decode it. This dot register, so we need the RD as well. Yeah, add. All right, so we need the RD as well. So the IMM7 is just IMM8 is just like the 8 lowest bound, and we already know we need to shift them left because we add these 2 zeros. And then RD is just opcode shifted by 8, and then we just want 3 bits, right? Where was that? Yep, 3 bits. And then these registers RD equals this.sp plus IMM. Actually, let's say stay consistent with the datasheet. The shift should happen here, like this. This is IMM8 without the 0 extension. So plus IMM shifted, save, and oh, IMM8. And it passes. All right, one more instruction. So let's. I wish I could strike it out somehow, but I don't see how. So I will just delete it. And then what's CPSID? CPSID. Primask PM. What is primask? Probably interrupt masking or something like that. Is there any that there must be something that explains about that? So primask, this page, exception mask register, priority boosting. Okay, whatever. So it has 1 bit that this all right. So for now, let's just, decode those instructions, but ignore them. I think they are like very simple. Where is the... Huh? There is like... I think these are not really instructions because I don't see like the decoding for them. It's probably MRS and MSR like are encoded into these instructions, or is there like... Actually, why are we working so hard? We know it's like encoded into this because we have this like value, so we can just say I still wonder about though, how comes it's not in the datasheet? Oh, they probably missed it, or maybe CPS. The system instruction, but they don't tell anything about encoding. Oh, this is synonym, not interesting. Oh yeah, there we go. CPS, and then yeah, so this is the encoding, and there is like 1 bit that says whether it's IE or ID, but we have like the value here, so we can use it as well. But let's make it consistent. Let's say like if it's this, just want to decode it. We don't need to test it right now, just so we don't get the noise. Maybe we should still like else if opcode equals, oh, we already did like hexa, so I guess we can do it again. Forgive me for I have sinned. All right, so if it this one, let's just console log it for now, so we know we are ignoring it, and maybe in the future we'll decide that we need it once we understand what these are doing. And then if this is CPSID, then CPSIE is probably 1 bit set, so bit number 4 is supposed to be 1. So, oh, that's actually the 5th bit. So this should be, oh, I think it's set here. Oh, wait a second. I think this bit is set. Yep, it's 1. So maybe effect I am. Oh, IE is 0. Got it. So we need to turn this bit off. Okay, that makes sense. So basically, instead of 7, that would be 6. Let's just verify that I did the math right. And yeah, we can see this bit is off now. And this is ID with the bit set, CPSIE. And we are done with this instruction as well. And then we have a few more. LSRS. Didn't we do it last time? No, we don't have LSRS. Probably another kind of shifts. Logical shift right immediate. Okay. There was like immediate and register, and don't we have a shift right? We have LSL, LSLS immediate, LSLS register, and LSLR. What's LSLR? LSL. Okay. Okay, let's do LSRS. LSRS, where are you, LSRS? LSR, so let's do the usual stuff. Assembler, LSR. We do have the encoding for LSRS, right? LSRS. But we haven't implemented it yet. Did we do it last week or something like that? Probably we implemented the encoding. LSRS register immediate, register immediate. Seems good. So we probably did encoding, but we haven't implemented the actual instruction. So let's do that. LSRS. Huh? We have a test case. Something is, I'm missing something here. Maybe we have a problem. I think I know what happens here. We have the instruction, but we let's see in the git log. It doesn't say anything about LSRS, so maybe we did it and we forgot to mention it in the git log. And I guess if we focus, oh, we did focus on this test, we can see, yep, there is probably like, this is actually LSRS register, right? It's this one. Oh, wait, so this is LSRS register, right? And the one that we mentioned here is just 2 registers. Yep. So this is, but wait a second, there is an immediate here. Something is, oh, this is LSRS immediate. Okay, so now I get it. We implemented LSRS immediate. We didn't implement LSRS register, I guess. And then, yeah, we don't have LSRS register. I don't see it here. And then that's what we are missing right now. And we just didn't write a comment here. So that's that was a bit confusing. All right. So let's do the LSRS immediate. So this is actually LSRS immediate. No, we did LSRS immediate. Let's do LSRS register. Whew. Very confusing, all those names. LSRS register, and it takes RM and RDN. This is the prefix. And I guess the encoding scheme is the same as here, but you know, let's do the spec for that. So where was that? Yep, right. And the assembler spec, LSRS, and let's add a test case. LSRS, what did we have there? R0, R4. Should encode to this. And let's disable the test filter. So all the tests run. Okay. And we should just change it to encode LSRS register, the one that we have just implemented. And R0 with R4, it's green, perfect. So we got the encoding for that. And now let's see, LSLS, test case. So let's just take the LSLS and do a LSRS test case. LSLS and LSRS. So it should shift RM tells us how to shift, and then RDN is like doing the shift. And it's shifting in zeros. That's an important part. It's not shifting once, so it's a logical shift, not arithmetic shifts. So basically, let's do a test case that tests that. So if we had something like this, like we had 1 1 1 1 0 0 0 0 0 0 0 1 1 1 1, these are like this should be 16, or oh, wait a second, we want it to be, actually let's do it hexadecimal, otherwise so yeah, so let's do it F 0 0 0 0 F, and then if I, so ls right shift, so if I shift it RD, RN and RM, and it takes RDN, so that's the register I'm working on, R5, and I want to shift it by R0 byte, I guess the bottom byte of RM, like I did here, right? Yep. So basically this is ignored. This is the actual shift amount. Shift amount, that would make it probably easier to follow. So I'm going to shift it by 2 positions. That sounds fine. And then I expect the following. So the result should have, so I shifted it right by 2. So now this is 3 because like it inserted zeros. This is still F and this is C because the 2 bits from here shifted into this position. And then it's 0 0 0 0. And here two least significant bits shifted out, so it should be 3, just like this one. Yep. And then there is like there is carry. Yeah, carry should be true, I think, because carry is probably if we it's true if we shifted I guess a bit out. Let's just check it. Type LSR, so shift C. What does shift C do? Carry out. It was type LSR, so LSRC value amount, and carry out is shift extended X shift -1. Not sure actually. Let's see. Extended 0 extend X. So we are adding shift. So this has n bits, 32 bits. So we are like adding, extending it to have zeros as, I guess, to have shift zeros on the left. And then we are taking, oh yeah, so these are like the bits we are taking, and then shift -1 is like the next bit. So in this case, the carry should be true because the bit the last bit that we dropped was 1. All right, and then let's implement it. So that was, I guess, we already have the logic in LSRS immediate, so we just need to copy paste it and hope for the best. No, copy it down. So the second one is for register, and then the decoding goes as LSRS. Okay, so if this is this, and that was shift by 6, I guess. All right, let's just focus on this test, and we can also already see it gets here, so it means we are on the right track. And then I guess we can copy the decoding from LSLS register because they have the same operands. And then the logic is pretty similar, it's just RDN. And instead of, wait a second, where do we take the shift amount from? IMM5, so I guess instead of IMM5, how did we do it in LSRL? Okay, shift count, yep. So instead of that, we have the shift count, and then if we shift by 0, I guess nothing happens, right? Makes sense to me. Yeah, we can. I'm not sure why we had this if, but I guess. Wait a second. Something is strange. Why did we have this condition? What happens with LSRS immediate when the shift count is 0? Is there like any... Oh, wait a second. Decode IMM shift. Maybe decode IMM shift does something like... Yep. I guess this like had something to do. Decode IMM shift, case type off. Oh, that's but yeah, so shifting by 32, yeah, so I guess that's why we had this condition in that case, but I guess we don't need it here. LSRS register, we don't have any condition like that here, it's just doing the shift. So we don't really need to care about this case where it's 0. So basically input is just shifted, and then basically that's input shifted by decode shift. How did that get into my clipboard? All right, so I think that should work, but it didn't. Why is that? Expected something, received something else. Okay, let's result to string 16. All right, I can see the problem already. The input isn't registers RM, it's RDN actually. We are reading from we are shifting the wrong thing. Okay, but oh, wait a second. I edited the wrong thing here. Okay. Yeah, this is good. This is the immediate, and that's one is with the register. So why did they didn't? Anyway, let's remove the filter. This passes. Okay, so we haven't done any damage. And now I can do the right one instead. So, yep, this one. Okay, so we need to decode it, and then the input is RDN, and the result is just, we can ignore the input. We can just do it right like that. RDN, and shift amount is just these.registers RM, and we take the lowest byte, and the result is just shifting this and restore it to RDN, and then we don't need all this thing. We just take shift minus input shifted by shift amount -1. Okay, and oh, that's why we wanted to store it into input, but we can just, okay, let's call it input. All right, it passes. And now that I use this kind of shift, so in JavaScript we have like this shift, which if the most significant bit, if the sign bit is 1, it will add once, and this shift, which will act as a logical shift and add zeros, we can see it like, so if we have this value, or you know what, let's make it like this one. So this is the most significant bit here is 1, and we do shift, normal shift, like the 2 shifts by, let's say, let's shift it all the way, so 31 bits. You can see the result is -1, or if we convert it to unsigned and hexadecimal, you can see, or you know what, let's just convert it to binary, unsigned binary. You can see like, what was that? Too many parentheses. I will figure it out. Yeah, we need to add one here and remove one here. Not? Yes. Huh? Oh yeah, it just interesting. I got confused by the amount of parentheses. I don't need this one. Yeah, so you can see the difference. I'm not sure why it's not printing like, what's wrong, why it's not converting it to a positive number, even though I ordered it. Oh, right. Actually, doing this converts it to an unsigned number. So the trick is actually to use this operator again to convert it to an unsigned number. And now we can actually see that this was like shifted once all the ways when I use this operator, and when I use this one, it shifted zeros. And that's because here the most significant bit is copied as we shift with this two greater than sign operator, and this one always shifts in 0. And that's what LSRS should do. Anyway, so a quick side note about how these operators work in JavaScript. I think in other languages like C, it's always the arithmetic shifts, and never this like you only have this one and you don't have like something like this. It just doesn't exist. Anyway, so we got this instruction, and what else do we have? I think we had one or two more. So this one, strr1sp. I thought we finished with all these stores, but maybe there is a special one. str. I mean, there are just only 2 STRs, and I think we covered them both last time. So why did we have this on the list? Let's take a quick look at how many STRs did STR. We have this STR, R6 and immediate. Maybe register immediate. So why doesn't it decode it? Maybe we have a bug in how the decoding works, because I think this one, let's just remove the test filter, so all runs. This one should have also decoded this one, right? R1 SP 4 R6, yep. But let's take a look at the code. I think if it came up, we might have missed something. Oh, yep, I think we have missed something. Let's double check, but you see we are only taking 3 bits from the register, so obviously it can't address the SP, which is like I think that was SP 13. So let's see what we missed here. So that's str register. There is only one encoding. No, that was str actually with an immediate. Where was that? str immediate. So how comes there is like str? Oh, what is that? There is another encoding, but here it's, oh yeah, so this is the encoding that we missed. So we need to implement this one, str, and let's see if there is like an equivalent for LDR that we also need to do. So we'll do them both if we do. So that was LDR immediate, yeah. So LDR SP plus immediate. All right. IMM8. All right, so let's do the decoding first. str. That would be assembler spec and opcode str, and that was str immediate with, let's call it strsp. So strsp takes a register and offset, so R1, and the offset is 4 and 4. Oh, but I removed the opcode, and it should equal this. Cool. And now we just need to implement it. Assembler.ts opcode str. Let's do strsp. strsp. And then Wait a second. Why do we have copy it once, not twice? SDRSP, and it has like RT and IMM8. And then the encoding goes like this is all right. This is the opcode, and we have RT shifted by 8, and we don't need to do any shifts on the value of RT, just to move it 8 bits left. And then we also have this IMM8, and yeah, as usual, it's 0 extended, so we actually need to shift it to undo that when we encode it, and just take the lowest byte of the result, and it doesn't compile. Yep, using parentheses. Yep, and this is just 7 because it's 3-bit field, right? So yeah, so now let's and it doesn't work. SPR1 RT. So what did we expect and what did we get? 9101. One, and IMM8 should be 4. So what did I miss here? The opcode probably copied the wrong one, right? Yes, I copied the wrong one. You could have told me. Anyway, let's fix that. And it's still not ring though. RT IMM8, that's 8 bits, and there is this shift 011. So what's wrong now? The values seem closer, but it's still not what we need. And then, oh, right. Or no, this is fine. I think. Let's see if we have another one like this. Yes. Should actually this be very similar to this one? SDRSP. Yeah, it's basically the same as this one. I don't see any problems. So why do we have a problem with the encoding? What did I miss? Yeah. Let's see where I got a problem. Nine 901, so it's here somewhere here, like this is like 9, and this should also be 9. So why is it like 91 here? Oh, right, this is LDR, not SDR. I was copying from the wrong, looking at the wrong place. So that's why this bit is different. That's the difference probably between SDR and LDR. So where is SDR? SDR immediate. Yep. So that's the right. Finally, the right one, I guess. All right. So there we go. It's green. We are happy. And let's also do the LDR. We actually already did it without knowing LDR. And I mean, we could go into the code and look for a test case for that one, but since it's super similar to STR, I think that would be a waste of time. I hope I won't be proven wrong at some point, but basically the only difference, as we have seen, is this prefix. Otherwise, it's very much the same. I will just double check myself. So 111, and this is the encoding, and then we have RT, and then we have IMM, and it's also 0 extended. All right, now let's just implement those two and strike this one off the list. RP2040 LDR, so that was LDR SP plus immediate, right? Or plus minus immediate. I think add is true always, so it's plus immediate LDR, which makes sense because the stack goes down, so we want to look up the stack pointer. So all right, let's first add the test case. Okay, so this goes, where is this spec? Yep, LDR, and oh, what happened here? Someone got really mad. Let's restart the test runner. Oh, it got green again. Great. Okay, so LDR. LDR RT SP immediate. So let's say LDR R3 SP plus 12 instance. So opcode LDR SP with R3 and 12, and then we want SP P2040.sp to point, let's say, to the beginning of RAM, whatever, and then we can put in the SRAM in this location. So that would be 12 bytes into the SRAM. Let's put 55, and then after that we expect R3 to equal 55. Let's implement that. So LDR, that's SP plus immediate. So decoding it first. Okay, and now we have like IMM8, which is just the opcode and FF, and we also have like it's RT opcode shifted by 8, and then the other is just this dot sp plus IMM8 shifted by 2, and registers RT redoing. Okay, passes, perfect. And let's do also the same for STRSP. STR, where is the STR one? STR immediate, SPRT, SP plus immediate. So let's do the same pair of values, but this time we want to do the opposite. So RP2040.registers R3 equals 55, and then we expect the SRAM location to have this value. Right, let's make it more interesting. Let's put another byte just to see that it stores both bytes. Okay, and now let's implement it. So str, where is str immediate? So, and then str, write this, and we only need, we have the decoding. So basically, let's call it address. I think should be work. Oh, the opcode. That's the only thing we are missing here. We spent so much time on finding the right one, and yeah, this is green. Test passes. Yet another opcode. We are getting pretty efficient. We did I think in 40 minutes like 5 or 6 instructions. That's pretty fast. Let's do the last one just so I mean, if we get to that instruction, then it definitely means something went wrong. We shouldn't get there. So I want to know about this. And yeah, let's just do the encoding for that. So assembler.ts. I'm not going to do the test because it's a super simple one. So you know what? I'm not going to write a test for this. Just do the for now at least. We can always add it later. BKPT else if opcode 8 equals this thing, then console error breakpoint and IMM8, and then IMM8 is just the low 8 byte of the opcode. Okay. Yep. Cool. So we have that instruction as well. Not tested, but I honestly couldn't care less about testing it right now. So with that, I think we have everything we were missing last time. Let's, where are we? Yarn npm run start. Let's run the code and see what happens. We haven't run it for a week, and a lot of things happens, and we hit a breakpoint. And I think that's where we ended up last week, where we hit this breakpoint, and we were like tracing it. But now, if we open the output file, we can see there are like, I don't even remember if we used what do we do when there is a missing instruction? What do we print there? We have the word implemented. Yeah, so we have a single instruction that hasn't been implemented yet, and this is the opcode. And actually, you can probably debug it, figure out which opcode this is, but I'm not sure if we need it. But you know what, just for the sake of it, let's figure out what this is. So this is the opcode, and I wish I have seen that earlier, but they have like this table which explains about the instruction set encoding, so we can use it if we want to quickly decode an instruction given the opcode. So in this case, let's convert it to bits. So this is the, how can I copy this? Okay, so this is the binary representation of that. And let's make sure we have 16. So 4, 4, and 4. So yeah, let's see. It starts with 1, 0, 1, 1. So 1, 0, 1, 1. No, 1, 0, 1, 1. And then there is like 1, 1, 1, 1, 1. So it's miscellaneous 16-bit instructions. Okay. Yeah, 1, 0, 1, 1. And then we can like find which one it is. So this is like 1, 1, 1. The next, actually, I think the prefixes are like longer here. It's like 7 bits, right? So let's see. So the next 7 bits, the opcode is like 11111010. So 1110. That's breakpoint. Wait a second. No, that's hints. 1111. Okay, and then let's see what are the hints. So and then what do we have after the hint? We have like op A and op B. So op A is 0100. Wait, and then op B is 0000. So it's wait for event hint WFE. So this is the instruction. Let's double check. 1011 1111 00. Huh? That's not the same. Let's go back to where were we? That was 16-bit miscellaneous hints again. So this is like op A is 0100. So 01. Oh, that's send event hint. Okay, so that's like the instruction. That's the correct instruction. Let's double check. Yeah, the best way to double check would just be to copy this and see if it's the same. I think it is, but you know, we missed. We made an error last time. We wait for event. So yeah, this is the instruction that we find here, and I think this is like the only unimplemented instruction we have at the moment. And what does it do? Int instruction. Okay, so it sends an event to all the CPUs within a multiprocessor system. So it's a not compatible hint. So probably nothing we should worry about too much, but you know, let's just make sure we don't get his noise. Let's just edit. So that was sev, SEV. Yeah. Opcode equals this happy number. All right, so now we just know to decode it, but we still like don't do anything. We just print sev when we encounter it, and we can see that it found it. So cool. Yeah, and now I think we are still in this place where we have this breakpoint. And if I'm not wrong, we spent some time trying to figure it out last week, why it gets to this breakpoint, and I don't really remember. I think we were coming from hard fault or something like that. But that cut, I started thinking like when I did all this GDB stuff this week, that at this stage it would probably be helpful if we could use GDB to debug the simulator. Like using those prints to trace what's going on is nice, but it also requires a lot of we find I think we did it last week. We opened this output file and we open it side by side with the listing file. That was the disassembly file, and actually that's not Blink, that's I think yeah, That's, I think, the allow UART. And I think at the moment, the allow UART won't match, or maybe it will match, because I updated the SDK and the examples repo and rebuilt it with debugging flags. Let's just take a quick look. Yeah, you see it's like a different place. So if we want it to run, we should actually update the hex file that we have. Let's do that, so we can at least see. And it will probably still fail in the same way. Okay, no, it failed in a different way. Interesting. Oh, new unimplemented instructions. Interesting. So apparently updating the SDK did make some change here in the flow of the program, and we are no longer hitting the panic, which is nice, but we still have like a missing instruction. What's there? I thought we finished with all the instructions. Moves, we don't have that instruction. No, that doesn't match. Oh, why am I looking at blink? Hello UART.this. So here, MVNS. Yeah, I don't remember having seen MVNS, and that's the same opcode. So let's see if we have any other unimplemented instructions. They are all the same MVNS, and a lot of them, and it seems to be like stuck in a loop here. So maybe they just added a piece of code that uses this instruction and we haven't implemented it, so now it's even stuck. I think we are inside runtime init, just after clocks init. So yeah, let's see what MVNS does. MVNS Ooh, Bitwise NOT. Okay, so that shouldn't be too hard to implement. Let's do that. MVNS. Right. So maybe not having MVNS causes it to fail earlier, or maybe it doesn't fail where it failed before. We'll never know. But it doesn't matter. We're going to have this shiny new instruction in a moment. So opcode MOV sounds good. So MV it comes after MSR, MVNS, and then the thing should look like this. Let's do R3, R4. No, actually we don't have. Okay, so MVNS R3 and R3 should equal this magic number. Okay, and cool. And now let's do the opcode assembler opcode. So the opcode is just like MVNS, and it gets RDRM, RDRM, and it returns this shifted by 6, right? Yep, and then RM and RD. RM and 7 shifted by 3, and then RD and 7. All right, and let's import it. And green, perfect. And now let's do the test case. RP2040. That's not the test file. That's the test file. So MVNS. No, spec. That's what I wanted. So MVNS R3. Let's do different perf registers, just to see that we didn't do the encoding or decoding of the register number wrong. So our MVNS 4 gets R3. Okay, and now so the beginning we want to set CPU.registers R. So the input is RM, I guess. Yep, RM. So M is the second one, R3. So let's say the input is 111555. And then I think all it does is like bitwise NOT, and then updating the 0 and the carry. The carry is kept as like, I think we have seen that this just returns this if the shift T is LSN, and 0 we have it in a lot of other instructions. So carry is unchanged, and we only need to update those two flags. So basically, if we do the bitwise NOT of this, then that would be E, 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 A, and that should be R4. And then we expect it's not 0, so to be false, but it's negative, so negative should be true. Okay, and now let's implement it. MVNS. So I'll see if opcode shifted by 6 equals this big number. Then that's an MVNS. Then we should decode it, and probably similar to this one in terms of updating the flag. So let's copy that. And there is like RM is just and RD, right? RD is just the opcode and 7, and RM is like shifted by 3 and 7. Okay, and then we say registers RD is not RM, and let's place that into result. Bitwise NOT RM, that's bitwise NOT. Yeah, bitwise NOT. But this dot registers, not the number of the register, the actual value of it. So it gets the result, and then we do this, and it should work, but it works. It's green. Perfect. Missing instruction solved. Let's see what happens now. After we added that instruction, oh, interesting. We have some reads from invalid memory addresses, but it doesn't seem to be stuck anywhere, or yeah, it seems to be going all sort of places and running somewhere, right? Writing stuff. Oh, we are still missing an instruction. I thought we finished with all those missing instructions. Implemented. Yeah, ooh, a bunch of missing instructions. They just keep hunting us, right? Let's see what's there. So let's put them side by side and see what else we are missing. ASRS. So ASRS, I guess it's arithmetic shift. So that's one that we are still missing. And then there is like this one. What's this one? EORS. EOR is probably XOR, exclusive OR. We don't need this. And then what else do we have? Not implemented. This one's the previous one. This is a different one. What's there? SXTB. probably sign extend something. All right, and I think we visited that one, right? Yep, that one. And BA0B, what's there? Oh, that's the boot ROM. So we will need to do manual decoding again to figure out what's that instruction. Let's do that. So don't know if it's an important one, but we are doing it. But before we get further into implementing those instructions, which are probably important, I just want to keep running the code. Run link, even though it's not link. Let's do 20,000 instructions and see if we get code into some loop or what happens. Yeah, or was the output file? Doesn't look like 20,000 instructions because I haven't saved the file. Right, let's try that again. Now see what happens. Okay, we still got to this problematic point eventually, at some point, but a bit much later than before. Yeah, there is like a lot of code running before we get to that breakpoint thing, which happens to start just like those two instructions. So it will be easy to see it here. If we just select all the occurrences, we can see where it starts. So I think that's what we did last time. We figured out where that this is panic, this is assert, which is calling exit, and what's calling this wrap printf. It's returning. Okay, that makes sense because we called wrap printf. So where did we get into this assert function? That's the only occurrence. So we got here pretty early, but yeah, we had a lot of output or a lot of instructions going from the beginning of this until we actually called exit, which probably did the breakpoint. And where did we get to assert? IRQ set exclusive handler. So interesting. It seems like it's still. I remember this function, but I think last time we called a different function. So the thing is, maybe because this is a debug build, there are more instructions here. Like it's doing more stuff, and it's not inlining functions that were inlining in the original build. Anyway, we are still like in the same place where we couldn't get past this function. And I think in this point, so I was starting to talk about that before. What I would like to do, debugging like this is, I mean, looking at this output, this trace of the execution is probably pretty good way, as you have seen, to like see where things go wrong, because we can easily go forward and back in time and search for stuff. But then now we know where things that like we know that we got to this function and it did something that failed, some assertion that failed. And would probably would like to look at the values of the registers and understand what's going on here. And doing it with, adding debug prints like we did before here takes just a long time and it's pretty tedious and error prone. So what I would like to try to do is to try to make GDB connect to our simulation. And I'm not sure. I'm actually pretty pessimistic that we can finish it in the 1 hour more or less that we have today. but we can try, and we have like a bunch of instructions missing, like those ones. This one, let's just quickly, we'll do it in a moment. We'll decode it just to know what it is, but actually once we have GDB, that would be super easy to just tell it to disassemble that missing instruction, and then like we could use GDB to debug the simulator, which will make our life easier going forward to figure out like all those things that go wrong. For instance, we could just set a breakpoint here and see the stack trace and see things like we could even see like the values of C variables. We won't have to bother with registers. Like we would be able to see the C code next to the assembly code. So as I started saying before, I'm pretty pessimistic that we'll finish it in the hour or so that we have here left here. But worst case, I think we can finish it next week. I'm pretty optimistic that we will be able to. And we'll keep those instructions for later when we have the GDB capabilities. So actually, I have a better idea. One of the people watching this stream, I mean, I've done so many instructions, you know how it works. You can just try and send me a pull request, and if you need any help, I'm available on Discord. So I would love to see like a pull request with any of those instructions. I think they are all like similar. Maybe SXTB is a bit different. I think it's sign extend. Yeah, it's sign extends. Like I think implementing all of them shouldn't take more like 15 minutes. Maybe this one, we don't know what it is, but at least those three shouldn't take too long. So if you can just send a pull request, we'll have them ready for next week, and that will save some nice time, which we can spend on doing GDB. So let's do GDB. What we want to do is we want to have GDB instead of instead of telling GDB to connect like we did here. So instead of telling GDB target remote Raspberry Pi port 333, port 333, we want to tell GDB to connect to a port that we will open, and we will implement the GDB protocol. And for that, there is like a bunch of documentation about the protocol. But let me show you a cool trick that I learned. I think it was Steve Dometz, Utaboroso, that taught me that. You can do something like set debug remote one. And then if I do target remote localhost, not Raspberry Pi 3333, I can actually see a dump of the protocol. So I can see GDB is sending this packet, and then the OpenOCD, which is connected to the Raspberry Pi, replies with this packet, and then I can see like the entire transaction. So it makes it super easy, or not super easy, but it makes it easier to understand what's actually GDB is sending and expecting. We can see it sends information about the CPU and stuff like that. Anyway, let's start doing this. So instead of like doing it totally from scratch, I'm actually done something similar for the simulator in Wokwi. So if we go to GitHub of Wokwi, we can see there is like an implementation of gdbserver that connects to Wokwi, and we are going to use that as a basis. It's written in JavaScript, so it should be pretty easy to port into TypeScript. Maybe just add some type information. And some of the code here is not relevant. It's talking to a Wokwi WebSocket, but in our case, we're just going to plug it into gdbserver.ts and remove everything that talks to the WebSocket. So we don't need this WebSocket, we don't need the HTTP, and we don't need the file system. We don't need the SSL stuff. all of that HTTP stuff and WebSocket. We don't need that. Basically remove everything that is not related to GDB. And here we go. We have this function called gdbchecksum, and this function just, so if we take a look at the protocol, you can see that the packets, the commands, they start with a $sign, then there is a bunch of text, then there is a hash sign, and there is a hexadecimal number, and that's the checksum. And if we Google gdbserver protocol, there is probably yeah, there are like maybe GDB mode serial protocol. That sounds, maybe this is the right one, I don't know. Yeah, so there is like this very long document which I've read in the past, which explains, but you can see here they have this like format, which is $, and then the packet data, and then hash, and then the checksum, and then there is like an optional sequence ID. I actually, that's new to me. I didn't know that the, oh, prior to GDB5, so that's old, so we don't need to worry about that. All right, and then so GDB sends this, and we need to send plus as an acknowledgement, or minus to request retransmission. We don't need to worry about that because we are running locally. So this function just, you know, takes its text and calculates the checksum, and it's, I mean, you can check out later the code later, doing some JavaScript trickery to turn the text into bytes, and then it's summing the bytes, and then it's just converting this into an hex value. We don't need to worry about that. What we do need to do, let's change the GDB board to 3333 like on the Raspberry Pi, and yeah, update the years, and it's just RP2040 GDB server. Cool. And then what we can do is whenever there is a connection, so after we removed all the code, it's easier to understand what's going on here. We are requiring the net package, which lets us create a TCP server. We are telling it to listen on the given port. Then we have this function that, let's move it above because it's not really related here. Just a utility function that calculates this checksum. And then whenever we get a connection, hi Nekati, by the way, just so your comment. Whenever we get a connection, we can do something with this connection. So we don't need this. So basically, there is like a code that parses the input here and handles errors. We'll take a look at that in a moment. But first of all, let's make TypeScript happy. So GDB server is create server. Oh, maybe we don't have, yeah, well, let's convert it to an import, and then TypeScript will automatically figure the types for us, so we don't need to worry about it. We don't have walk-with socket, so we can remove it. Okay, and we don't need this if case, so we can always assume that there is like a connection, because we don't, I mean, we are debugging our own process, so we don't need this as well. Okay, cool. So the code is now green. We removed all the walk-with code, and just left with this code, which opens this GDB server, and then whenever we get some incoming data, it does what it does. And then what do we need to do here? So it does the parsing, it looks for the dollar, for the hash, checks that whatever it is, yeah, it does like some sanity checks that the hash appears before the dollar, or the hash doesn't appear before the dollar. I think we don't need to check. If we have a dollar in the hash, that's fine. and we can just look for the hash after the dollar. That's index of get position, yeah. So basically $+1, so it should appear after the dollar. Yeah, and hash +2 is like the 2 digits after the hash are inside the buffer. So we are basically reading data, appending it to a buffer, then we are just converting it from bytes. So it's a buffer of bytes. We are converting it to UTF-8 strings, and we save that in this buff variable. Then we are taking looking for dollar and hash, and if we found the dollar and later after it hash sign, and there are like at least 2 more characters after the hash sign, then we are extracting the command between the dollar and the hash sign. Actually, I think there is substring. JavaScript is confusing. There is substr and substring. So I think substring is more appropriate here, because instead of start and length, we give it start and end. But here it makes sense to use substr because we want just 2 bytes from this start. All right, so we extract this command, the checksum, check if this checksum of the command equals to the checksum that GDB sends us, which should be true always. But if it's not for some reason, we send a minus, which is means that it's the opposite of acknowledge. It's like request retransmission, tells GDB we are not happy. Otherwise, it tells GDB okay. Plus means I got it, and then does nothing for now because we need to process the message. So the next thing we need to do is like write this logic that let's set debug to true so we can see what GDB sends, and then we can actually run this and see what happens. Let's add another npm script calling it. Actually, before we do it, let's just commit what we have done so far. So rp assembler, and we have a few more instructions we did today. So yeah. So we did, what did we do? We did add sp. And we had like, we'll look here, that would be quicker. Huh? Why do we import rm? We don't need it. Sometimes Visual Studio Code just import stuff, and that's why I like to review the code before I commit, just to find this kind of strange things that it does. Anyways, so we did add, and what else? BKPT, sort of, and CPSID, CPSIE. Okay, and then we did LDRSP plus immediate, and then we also did LSRS register, and then we also did like MVNS. I think we had this sev, which doesn't do too much at the moment, and then we had this LDR, which we already, and then that was like debugging stuff we don't really need. And I think we did some str as well, haven't we? I remember we did some kind of str. Maybe we forgot to update the comment. Oh, yep, it's LDR strsp plus immediate. Okay, let's do it. So yeah, you see, it's good to check before you commit, because otherwise you can commit bad things like invalid comments and debug stuff. So yeah. Okay, so we added this and still missing. Hopefully someone will, or someone please send a PR during the week. So we have those ones which are missing. So reminding you, the first one is like the encoded instruction, and this is like the meaning of the instruction, like the assembler name of it. All right, so let's commit that and push that. And now once we finish that, we can start working or continue working on the GDB server. First thing I want to do, I just let's close this. We don't need it anymore. It's in the commit message. Let's add a new script. We call it start GDB, and this will start gdbserver.ts. And then we can run it yarn start GDB or npm run start GDB because we use npm here. Okay, and it's running. Maybe it's a good idea to print something when we are running. And actually I'm going to install something that will be helpful here. It's called tsnodev, and it's similar to tsnode, which runs TypeScript code in Node, but it also automatically reloads the code when we make changes. So it's pretty useful. A second, it doesn't like the fact that npm and I both messed with this, so tsnodev. And now I can do this again, but instead of dsnode, I'm going to use tsnodev, and you can see that let's say I'm not happy with the fact it's not telling me anything when it starts. So I can add console log gdb rp24 gdb server ready, listening on port, and then that's gdb port. And you see, whenever I save, it just restarted the script, and I can okay, it should be gdb server. Yeah, and it's really nice to iterate this way. And now I have the GDB server, and I can try to connect to it from the GDB. So that's one of the things when you work with WSL. You have to get the IP of the Windows machine when you want to access it from the Linux. That's with WSL2. With WSL1, it would just have worked, and probably blocked by some firewall rule, or I don't know, maybe it's not listening correctly. But yeah, it doesn't work. So what I'm going to do, I'm going to cheat here, and I'm going to run this script inside Linux. Again, WSL things. So let's just do the same inside Linux and hope for the best. It's a bit slower because the file system sharing isn't super fast, but now I can just connect to it as localhost. And yeah, you can see that GDB sent us some stuff, but there is like checksum error. Yeah, so the first thing we do, set remote, but it connects, that's a good start. Set debug remote 1, and then let's see what happens. So GDB sent us this packet and got NUC. So why did we have NUC? Probably I missed something here. Oh yeah, of course. This should be the CMD, the command. You see, it's just one byte. Should be from the $$ into the hash. So I saved, but now I think inside, when I'm running inside the Linux Visual Studio Code, the yeah, the auto reload doesn't work. Yeah, I should have probably moved this to the Linux file system, but anyway, I will just restart it manually for now. So yeah, so we can see that now GDB is happier, like it's sending stuff, and we got still checksum errors, and I think the reason is we are still missing one. Yeah, it's probably end non-inclusive, so we are still missing like the last. You can see it sends empty and it gets, so we are missing the last byte. Let's retry that again, and hopefully at this point we will be able to, yep, we can see that GDB sent us this message, and now we should answer that. And it sent us another message, and we should answer that as well. So let's add a function that processes the the incoming GDB message and sends a response. Let's call it response calls GDB message, or process GDB message that gets the CMD. And if we get a response, we just write it back to the socket. So write response. Otherwise, we don't do anything with that. And then we can implement the second function. Let's call it function process GDB message that gets text or CMD, and it returns a response. And now we can start looking at the CMD, and according to the command, we can do things. So there is like this first command, Q supported. And where is that? Q supported. That was, I guess, somewhere here in packets. There is probably the, yeah. So yeah. So I guess the Q is for query. If I'm not mistaken, each command is like the first letter is the command, and then this is like the parameters or data, and Q is like query. You can see here all the list of commands, I guess. Q, yeah, query and set, general query packets. So yeah, and I guess Q supported, yeah, it tells the remote which features are supported, and it's like name equals value, name plus, name minus, and we should answer that. Like we can see that there are like a lot of things we can support, and I think we can just try to reply with an empty message and see what like tell GDB that we don't support anything, and see what happens. If we scroll up a little, we can see what the actual OpenOCD GDB stub replies. So we can say Q supported. So it's just a list that yeah, have like those semicolon separated things. So first of all, let's say we wanted to return an empty string, but we also need to add this dollar and the checksum. So basically we need to do something like dollar and then hash and then GDB checksum of an empty string. Let's see how this goes. So remote localhost. Oh wow. Just by replying with an empty package to everything, you can see we got pretty far. I mean, yeah. So you can see that it's on this Q supported. Supports packet is not supported, okay, but GDB goes on. Status, trace status, it sends us all sort of like queries, and we just answer with empty packets, and it's happy. until it sends us this packet, and it says bad register packet. So probably this command, we do need to handle it. But what I'm getting from here is that we sent the response was formatted correctly. So that's a good sign. And then let's take a look at this G command. So G, where is this G? Need to search for it. Yeah, read general register. So this command, like the G that it sends to us, you can see here, is asking us to just report the value of the registers. And at the moment, we don't really have any instance of the simulator. So let's first start by switch cmd0, so checking what byte it does. So the default would be, if we don't recognize the command, we just reply with an empty packet, because that works. But if it's G, then we need to report the registers to GDB. So that would be something like, how would we do that? So it says that each byte of the register, 2 hex digits, target, GDB internal GDB arc function, deprecated register row size. Okay. Okay, so it expects like list of hex encoded values for each of the registers, and I guess we can probably do that. Let's try to reply with just, actually, I'm going to turn this into a function, gdb response value string. We just returns this value with the $, the hash, and the checksum of value. So we don't have to repeat that everywhere. So basically this is like gdb response, and we don't need that. This is just gdb response with an empty string. And for G, let's just answer with zeros and see what happens. So just sending zeros as if the whatever register is 0. Okay, and then let's connect to our improvised server and see what happens. Nothing. Oh, it wasn't happy about something. Oh, right. The response is we are returning a string, I guess. No, why does it say we are returning a void? Actually, we are always returning a string, right? Oh, I get it now. GDB response, we need to return this. That's why TypeScript was mad at us, and it says it was returning void because we didn't return anything. So yeah, thanks GDB TypeScript was mad at us. Thanks TypeScript for catching this, and let's try again. And voila, invalid remote reply though. Why does it say invalid remote reply for sending packet received? That's console log also what we are sending. So if debug console log response. Okay, debug. I need to spell it correctly. Okay, and now we can try that again. Actually, I think we destroyed GDB. It's just stuck. Okay, let's start a new GDB then. Set debug remote 1, target localhost remote localhost 333. Yeah. So it doesn't like it when it just received 00000. It kills GDB. it thinks it's an empty packet, though it says. Is there like an example? Yeah, there is an example. It's just a number of zeros. And okay, let's do this. Let's see what the real Raspberry Pi sends. So we destroy GDB, target remote. Okay, set debug remote 1, target remote Raspberry Pi 3333. Okay, and now we can just see this is the reply the Raspberry Pi sent. So let's just try to send this as a reply and see what happens. And then we can figure out what each of these entries means. Sort of reverse engineer our way. Okay, so let's start this and then target remote localhost 333. Yes. Still doesn't like it. Invalid remote reply. What's the reason for that? It's the same one as it got, I guess, here as a response. It sends G, and then it received this one. Started with many zeros and ending in 21. Interesting. Let's try to also send the same result for Q supported. Maybe something is, it doesn't know. Actually, I'm going to try something else first. So this is multi-arch GDB, and I don't know how it knows. It might need one of those replies to figure out that it's working with an ARM microprocessor. I'm not sure. Like this one, target XML, seems like something important, probably. But I also have here, maybe that would speed up the development for now. I also have here like GDB ARM GCC. GCC ARM. All right. So I also have like ARM GDB, ARM non-EBI GDB, and then we can try to use that, and that runs on the Windows machine, so we don't have to worry about those these like running it in WSL and stuff. Okay, so remote localhost 333. Oh, it dies on the same thing, even though I think it dies before. It sends a different message. It didn't send us G, it sent us Q attached, and we sent an empty reply. So I guess for Q attached, we shouldn't reply with an empty reply, right? Let's see. This is probably throwing it off, and I guess we should say we are attached. Is there like a Q attached here? Yep. So yeah, so the answer is 1 for that. So let's try to implement that. So case Q, if CMD equals Q attached, then just return GDB response 1, else return GDB response empty response, because we didn't know that. And now let's try that again. Let's run it in the terminal. That would be more convenient. GC ARM bin ARM GDB set debug remote 1 target remote localhost 3333, and query attach is supported. Oh, it's still getting this invalid remote reply for some reason. I wonder what we are sending there that makes it bail. So if we have a response, then we print it and we send it. And I think we probably sent a response that looks correct, and queue attached packet received 1. If it's received, it's probably meaning the checksum is good. So I'm not sure. Maybe we should still implement this queue supported. Let's try that. Okay. So if CMD starts with queue supported, return GDB response, and let's just respond with whatever the real one response. That's this. All right. Without. Okay, let's try that. And then I think it really kills GDB when we send it in invalid remote reply, like task kill / what was the name of that? It was arm non eabi gdb gdb.exe, maybe /f/im. Cool. Oh, think I sent it the wrong packet, the wrong reply. I think I sent it the request, not a response. So yeah, let's go back. Yeah, that's the response for queue supported. Not I sent it the request instead of this response. So let's try that again. Target remote localhost 3333. Add. Oh, nice. I mean, I'm not sure if it's nice, but yeah, maybe we should just let's remove all of those and leave just the packet size. Maybe it needs to know the packet size. So, and no, still invalid remote reply for the queue attached. So maybe we'll start looking at the other ones, like let's try to see. So HG returns, if it's HGFS, HG0, it returns okay. So maybe we can do it like that. If CMD equals HG0, then return, or that was lowercase g, return our GDB response. Okay. And what else did we have? It sends Qt status. Where is this Qt status? Let's see here, a Qt status. We are sending this when we are getting, when the packet is, oh, there is like, it sends a question mark. So when it sends a question mark, we need to reply with this. I think, if I'm not mistaken, that says that what's the GDB response. So this means S05, right? This means we are stopped in a breakpoint or something like that. What else does it send to us? Qt status just before this question mark. And it's the real OpenOCD replies with an empty packet, so that's fine. We can do it too. Thread info. Does it ask for thread info? That's right after a question mark, so maybe it uses different command. And okay, let's just, you know, we did a couple of changes. Let's check if it improved the situation. target remote localhost 333. Hooray! It doesn't die. It's still not happy. It says truncated register 16 in remote G packet. But now let's try to see if it works. Let's switch back to the Linux version because that reply worked with the Linux version. I don't know. Maybe it will work, maybe not, but let's try that with the Linux version. Okay, so target remote localhost 3333. Oh, wow. Wow. Yeah, it connected and it's happy. I mean, we are not sending it anything interesting, but you see, it's like it knows where we are, and I think it took the same offset. So this value here is probably appearing in this G response somewhere. Like I can look for it. It's probably Little Indian. So yeah, so it got this value from here. Let me double check it. I will just change it, let's say, to FFFF, and then I'll restart the code. So now I'm expecting it to read 00FFFF. Yes, reconnect. Yep, actually FFFE, because the LSB is always cleared in ARM thumb. We know that. So yeah, so I got GDB to connect successfully to my code, which is quite amazing. Now I just need to, so if I do info registers, I can see I get like a dump of the registers, but this is garbage. It's reading it from this response, but I have no idea which register goes where. So we'll have to figure that out, but that's a great start. GDB connects, and it issues a bunch of M commands. You can see here, and those MF offsets that correspond to the value of PC. And I think M is like reading from the memory. So let's see that. So yeah, read length addressable memory unit starting at address header and at the given offset. So we can also try to implement that case M. So in case it's M, we have like the address and then a comma, and probably everything is hexadecimal encoded. It doesn't say anything, but since address is encoded, I guess this is also encoded, so we can just decode it. So so let's say params is cmd substring 1, and then maybe we can also split it already by the comma, and then address is just params 0. And we need to convert it to from a string into a hexadecimal string into an integer address, and length, and that's yeah, that's also the second. Let's const log reading from address count lengths. Cool. And I think if we look at the GDB at the output from yeah, you see it's reading like 2 bytes from the real Raspberry Pi Pico. It's reading either 2 or 4 bytes, and the replies are just like the hexadecimal dump of those bytes. So we would need to do that, and in order to do that, we need to have an instance, to create an instance of the debugger. So let's do that in this GDB server. Let's const rp2040. Let's create it above before we started GDB. Process GDB message. Yeah. new RP2040. Okay. Next, run blink. So we need to load a file. Oh, we need to load a hex file, and then we can create it with a hex file. So we need to import fs as well. Okay, great. Good. So, and then we can load the hex file, and then we can just, when it asks to read the registers and read the memory, we can just return the current state of the simulator that we have just created. So whenever we want to read from the memory, for instance, we can just let result is an empty string, and then for let I equals 0, I goes from 0 to length, I plus plus, and then RP read unit address plus I, just reading from the simulator memory, and result plus equals, and then this is like a number, and we need to encode it as hex string as GDB expects. So encode hex byte. Let's implement encode hex byte. We don't have to worry about doing this, because this is something GDB checksum already does, so we can just refactor. So basically this line, move it here, and then instead of doing it here, we can just... This is also a quick way to check that this is correct. I mean, this is correct. We copied it from GDB's checksum, and we know it adds the hex byte at the end. So I think, oh, and then return GDB response of the result. So yeah, so I think that should probably do the string. Should do the trick, not do the also the string, so we can read from the memory. Cool, and we have a debug string, so we can see if it works. And then we need this to return the registers, and we still don't know which register is which. So what I'm going to do here is that was this GDB. So I'm going to sort of try to reverse engineering this, so we can see a few values here, like this value, and we know this is R6. So if we look for it, and remember this is little Indian, so we have to reverse the bytes. Yeah, so this is where R6 is. Let's write this down, so we know this is R6, R6, R6. Okay, yep. All right, so this is where R6 is, and then we have a few Fs, and it makes sense that these are two registers, R5 and R4, and then we have these, what is that? This is probably R4 and R5, so this should be 1, 2, 3, 4, 1, 2, 3, 4, R3, and let's verify that. So this is 0170. Again, Indian stuff. So yeah, we can see it's 0170. So that's correct. And then we can see here the 2 from R2. And we can assume this is like R1 and R0. So basically the basic registers are just like, so we have here R1 and then R2 somewhere. Wait a second. R2, oh, R0. Now that makes more sense. R1, this is R2, and then R3, R4, R5, R6. And then if we continue like that, we'll probably get to, so we expect to see here like this 04 from R7, and then a bunch of Fs until there is like a lot of zeros and FB for R12. Let's try to find that. A lot of zeros and the B, right? FB, yeah. So this is R12. And then this is probably R13 LR. R13 is the stack pointer. Yeah, so that looks like a memory location to me, and I think this is it, right? That was 20041EE8, 20041E8. So this is like SP R13, and then there is like LR, which is just a bunch of zeros and 0127. So this is LR R14, and then we have this. We already know it. It's like PC. And then there is like one other value, which I don't know what it is, but it's probably this XPSR, because that's the only remaining value and it makes sense. So now we know how this string works, and we can probably just write everything into a buffer. So we have like 16 values for the registers and this XPSR value. So we can create a new buffer. Buf new uint 32 array. So we have 17 values, and then we can just say, actually we can just it's like the same order as the register. So we can say buf.set rp2040.registers, just copy the value of all the 16 registers, and then buf17 XPSR, which we don't have at the moment, so it will just be 0. And finally we just need to convert it like we did here into so let's just take this function, make a function out of it. So let's call it function encode hex buff. It gets a byte array, uint array, and what it does, we can do that like that. Return array from, just convert it into a standard JavaScript array, and map each element should be transformed by the encode hex byte and join it. So we are just going over the elements of the arrays, encoding them to bytes one by one, and then just stitching the result together. Very functional code. All right, and then we can say something like this. GDB response just takes the code hex buff with buff, but we need to convert it to a uint8 array. And that's how we do it with JavaScript. And if we did everything good, now we should be let's just, for checking, let's set buff, or let's do it at the CPU level. rp2040.registers R5, let's set it to 1 2 3 4, and PC, let's set it to a legit address, so something that looks legit, something somewhere inside the bootloader. All right, I think I got too many digits here. Yeah. Okay, cool. Let's restart it and see what GDB thinks if we got it right. Yes. Ooh. Okay, we need to reconnect. Nice. So yeah, you can see that it figured out the PC correctly, because that's the value we set. Let's do info registers. And all the registers are 0 except for SP, which was probably initialized to this value. I think we initialized SB to this value somewhere here. Or maybe, yeah, we are reading it from the boot ROM, so that's probably the value. So that's cool. And okay, where were we? And there is like this 1, 2, 3, 4 that we have set just to test things, and that works as well. Cool. So if we type where, it does a lot of reads from the memory and it doesn't figure out where we are, and that makes sense because the stack is empty. But if we do this as, we can see this assembly, and I'm not sure if this assembly is legit, but we can see it reads from the memory. Let's try to disassemble an address that we know is legit. Let's say we had, let's see what's here. This AS, yeah, hexa. Yeah, so we can see it's starting to read stuff from the memory, and I think we are actually using the wrong L file because we are debugging the hello UART, right? We are loading the hello UART here, but I think GDB uses the one for Blink, so let's use the right one. UART, hello UART. Hello UART.elf, target remote localhost 333. Right, still the same place, but now if we disassemble this address, we will probably, oh, without the, interesting, oh, plus. Yeah, actually the same function. I guess this is the correct function. I'm not sure. Let's take a look at the disassembled file just to compare it with, where was that? With the output here. Yeah, I think it's the same code. So yeah, so we can already use GDB like to start disassembling stuff. And there was this one single instruction that we weren't sure about, like not implemented. So this one, which was somewhere in the RAM. So I think right now we can't really disassemble it because we haven't run the simulation yet. So there won't be anything in the RAM. But what we can do now, we can run the simulation before GDB starts. So just like we are doing here, just set MCU to PC and start running stuff. GDB server, so where is that? Yep. So let's call that. We don't need all those logs. We are just going to run a bunch of instructions. Cool. And then we'll restart this. And then now when it starts, it should execute 20,000 instructions. And now when we look at GDB, a lot of outputs. Don't know why I stop it, but remote localhost 3333. So now, oh, yeah, I forgot to remove this part where we are overriding the register and the PC. So we are seeing the wrong thing right now. So let's retry that. Now it's loading, running the simulation, and eventually printing a lot of stuff. Now we can see that it's stopped in the right place. I mean, if we type where, we can probably see the entire stack trace where that got us to it's cool to see all this output. Yeah, we can see the entire stack trace where we are at exactly that got us into this exit. So we know exactly where we are, and we got all of that just by and we can just, like, you know, inspect the registers and maybe even let's try that. Yeah, I think we can see like the parameters of the functions here. I think like 3, I guess this is, and the pool. So yeah, so see how far we have got just just by, we spent 1 hour less on getting GDB to connect to the simulation, and now we can already, when we crash or when we get to some point, we can already see a lot of more information instead of like manually hunting for it. So GDB knows it knows like that the assertion that failed was from this file in this line, and this is the function, and this is the assertion that failed, and we no longer have to hunt for it in the source code. And we can also like so I wanted to disassemble and see what was this instruction that we didn't have. So let's try test this as I see there are a few nice. I see there are a few comments in the chat from GSM. So yeah, I'm not exactly injecting a GDB stub into the Pico. I'm injecting a GDB stub into the Pico simulator. And thank for the comment about the GPSR. It's like APSR, which is the flex, EPSR, and IPSR. So I'll write that down so we can. I think it's not really important right now, but we'll get back to that at some point. That was here. We don't need this break because we already returned. That was in the G. So yeah, so buff 16, 0. PSR, which is okay. So maybe to do. So right now it's always 0. We can see here it's 0, but it shouldn't be. And yeah, hi Jam from Amsterdam. Nice to see you here. And Jam is asking if he can download Windows Mini for the Pi Pico instead. I don't know. You can try and tell me. Anyway, let's take a look at this location and see if we can figure out what's there. And interesting. Read from invalid memory address. Why is it trying to dump? Oh, without a star. Okay, so now we can see the instruction that is in this enter address, which is RAM address. Something copied this code into the RAM, and we can see that the missing instruction here that we had in the code is xxtb, which I think we already have on our instruction list, right? For the next time. SXTB R2, it's the same one. Maybe it's actually the same code that somebody copied into the RAM. And you see how easy that was once we have GDB to figure out what's there, even though we don't have, we don't, at this point, we don't need this disassembly file anymore. We can just work with GDB and do things much faster. And I'm so happy we did it. Like, it's still not like a complete debugger. We can, I mean, if I try to step or something, GDB breaks, but that's definitely something we can, yeah, where is the output of that? Yeah, it recognized that we had a break, like we sent Control-C from, oh, it doesn't break, it just needs waits for us. Anyway, so we still haven't implemented stuff like stepping and continuing the simulation, but we can do it next week. But even what we got so far is so useful, because now we can just use all the power of GDB, and it has a lot of power to figure out what goes wrong with the simulation, which means that our future debugging sessions are going to be much faster. And it took us just 1 hour to get in there. I'm super excited we did it, and I feel like we should have done it before, but at least we have it now. And as an added bonus, we can also talk to the OpenOCD on that is connected to the Pi Pico. So we have a setup where we could compare the same code on the simulator and the real Pico, and we didn't have that before. So I think that gives us a lot of power for our future sessions. And I think that would be a great time to just commit what we have today. So all this gdbserver implementation, let's stage it. This one, we don't need it anymore, I guess. And this is just the tsno dev. We'll probably get rid of the tsno dev at some point. We don't really need it when we are actually, even now we don't really need it because we are working on the Linux. It doesn't work anyway, so I manually restart it whenever we are making changes to the GDB server, but eventually this will be stable and we won't need to restart it. We'll just connect to it from GDB. So yeah, let's take a quick look if we have anything. I think it's good. Yeah, great. Okay, so fit GDB server, add GDB server, and let's put a party emoji because that's how I feel today. And yeah, this is the first time we have 2 commits in one session, and let's push it. And yeah, I'm pretty happy about our progress today. We have 3 missing instructions and 1 thing to still to investigate, at least, like this IRQ whatever function that goes wrong. But now we got much better infrastructure and tools to do it. And I would really be glad to see a pull request for those missing instructions. So you can find them in the Git log. So you can just go to github.com, workwe rp2040.js, and go to commits, and there it is here. So you can find them here, and if you can do that, any of you, for the next week, I would be grateful, because we won't have to spend like 10 or 15 minutes. It's just those 3 ones. This one is the same. So just 3 instructions, and we want to have to spend that time next week, and we can just we will be able to continue with debugging GDB server and making it actually useful to step through the code and do whatever. I feel we are already we got quite nice progress today, and I hope to keep the pace going like this next week. So anyway, I hope that you will have a great week, and I hope to see a nice pull request for those instructions this week. And if you have any questions, you can always GCM had a good comment here. I will add it here so we won't forget it next week. Yep. So cool. And so GCM is asking if I needed to get UART working to get this tab working, and the truth is I didn't. If you want to get GDB running on their real RP2040, you have like GDB stub that you can install on the don't remember where it is. There is like some GitHub that you can Google that later. There is some GitHub that you can upload, include in your code. But in this case, we don't need any UART or anything. This is like code running the emulator, so it can talk with the GDB, and we don't need any stub. So thanks for the comments in the chat, and as I said before, I will see you next week. I hope to see a pull request for those missing instructions. I'm already looking forward to get GDB to do even more work for us. And until then, have a great rest of the week. And if you have any questions, just catch me on Discord, workwe.com/Discord. I'm there all week, so you can chat with me there. So have a great week, and goodbye. See you again next time. Bye bye.